No.
My name is Meng.
No, let me open the letter. So your name is Meng.
Yes. Okay, thank you for the introduction. My name is Meng, and I'm a student in UNC at Chapel Hill. Today I'm going to introduce a group, work in our group. This work is about joint labeling of multiple regions of interest by enhanced auto context model. Because the authors are not here, I will present it on behalf of them. So ROI labeling in brain image is very necessary because accurate quantitative measurement of morphological structures is important in neural image-based studies. And we want to label multiple ROI jointly because spatially adjacent structures are highly correlated to each other in terms of their brain functions or changes due to the disease. Recently, multi-atlas-based labeling methods are proposed. The basic idea of this method is assume we have a number of atlas, and given the new image, we first register all the atlas to the new image using the deformable registration. After that, the label information can be propagated to the new image and fused together. The most advantage of this method is using multi-atlas-based method can recover the huge variance across subjects and also reduce the bias compared to just using one atlas. But it has two problems. The first problem is it needs accurate registration, which means the quality of labeling highly depends on the accuracy of the registration result. The second problem is it is difficult to accurately label the voxels in the boundaries of neighboring ROI because each ROI is labeled independently. Meanwhile, there is another kind of labeling method named auto-context model, or in short, eACM. It is a learning-based method, and this method does not need accurate registration. Basically, this method can extract the context features from the output and use these context features to upgrade the classifier, and using new classifier, the output can be refined. Also, the context feature can be extracted again, so the output can be iteratively refined. Unfortunately, this method is designed to use for labeling only one ROI and cannot be used in the framework of multi-atlas-based segmentation. So in this paper, we propose enhanced ISBI to label multi-ROI jointly. Specifically, this method can simultaneously train ISBIs for neighboring structures. And when we update the output labeling map, we will use multi-scale representation. Finally, we integrate this ISBI into a multi-atlas framework. Okay. First, I will talk about how to use conventional ISBI to label only one ROI. So given the training image, which are pre-labeled, which are already aligned together, so we can extract three kinds of features: the appearance features, or text features, and context features. Note that the context features are extracted from the initial probability maps. Using this information, we can train the first classifier. Then we apply this classifier to the training images, and we can get the new probability maps. So the context features can be extracted again from the new probability maps. And of course, we can get the second classifier. We do it iteratively, so at the end, we can get a classifier sequence for labeling this single ROI. And in the case of multiple ROIs, each ROI can be independently labeled using the same method. But as I just introduced, because neighboring ROI may highly correlate to each other, so the result of labeling one ROI may be very helpful for labeling the neighboring ROIs. So in our method, when we compute the context features, we will not only extract the context features from the current ROI, we will also consider the context features from the neighboring ROI. In this way, the neighboring information can be used to help improve the performance. So the most important thing here is the context features. So next, I will introduce how to extract the context features and what is multi-scale representation. So this figure shows a traditional way to extract the context features. There are 3 probability maps, each probability map corresponding to an ROI, and the context features are extracted from the probability maps. The context features is just a vector of mean probability value in the blocks which are sampled in the neighborhood. So traditionally, all the blocks will have the same size, but in fact, the blocks with different distance to the center should have different importance. So in our method, we do it adaptively, which means for the blocks near the center, we will use the small size. And for the blocks far from the center, we use larger size. So in this way, the voxels near the center will have more weights than the voxels far from the center. Also, before we extract the context features from the probability maps, the probability map will smooth using different Gaussian kernels, different size of Gaussian kernels. So at the end, we will have the context features with different levels of details. Okay. Next, I will talk about how to use this eACM in a multi-atlas segmentation framework. So in the training stage, assume we have a lot of training images. We can pick the first training image out and align all the other training images to the first training image. After the alignment, we can trade a sequence of classifiers for each ROI as I just introduced. And note that all the classifiers right now are in the space of the first training image, and we call this space atlas space 1. Similarly, we can align all the training images to the second training image. So we can get classifiers in atlas space 2. So if we have untraining images, we can get the classifiers in atlas space. In the testing stage, the testing image can first align to the atlas space 1 and use the classifiers to get the probability maps or the classification maps. Similarly, we can put this test image to other atlas space and get the classification maps. So for each ROI, we will average the classification maps. And finally, we use level size to merge all of them together to get the final segmentation. Okay. We apply our method on this lonely data set. There are 40 images in this data set, and each image will have 56 manual labeled ROIs, which is 20 of them as training images and 20 of them as testing images. We evaluate the segmentation from performance in 2 groups of specially connected ROIs. So this is the result of the first design. The first figure is the manual labels, which are the ground truths, and the second figure is the label result by conventional ISBI. The third figure is the labeling result of our method. We can see our method is better, especially in the area of near the boundary of red region and blue region. This is the result on our ISBI 2. We can get the same conclusion. If you see the blue region, you can see our result is much better. And then here is a quantitative evaluation. We use 4 matrices: the precision, recall, jackpot, and death ratio. The green color bar stands for the output of conventional ISBI, and the red bar stands for our result. And it is clear that for all metrics and for all ROIs, our result is better. So here comes the conclusion. propose eACM for labeling multiple ROIs, and specifically, this method can train exam simultaneously and cooperate all the exams. When we update the output probability maps, we use multi-skill representation, and we integrate the exam into a multi-atlas framework. The experiment result shows that our method can achieve more accurate labeling results compared to the conventional exam. Thank you for listening.
Okay, thank you. Speakers, no questions? Any questions? I have a question for you about the evaluation. Were those statistically significant differences between your method and the comparison techniques? And that's why.
Yes, because this paper didn't provide the p-value, so I don't know whether the performance is significant. But at least in this figure, you can see the improvement is obvious, so you can see it clearly. And moreover, we not only compared to this method, we have some other results that not shown in the paper. We compared it with the other previous studies and also show the longitudinal.
Any other questions?
My question to you, you were talking about those multiple classifiers to train in parallel. You train the classifiers in parallel.
In parallel?
But when you have multiple classifiers, then you average the results.
Yes, but it is not launched parallel because in each step, the classifier should communicate to each other.
Can you open that slide, like 3 slides back or 4 slides back?
Yeah.
This one, okay.
You mean this one?
Right.
Okay. This one
So the
will be.
classification map which you are showing now, if you go to the next step, the next classification map, they are not independent. That's what I meant by now. If you independently train for different classification maps, and I think the best is that you combine them by average. Am I right or wrong?
Okay. So let's first repeat your question. So you think if you do it independently and then at the very end merge them together, do you think the performance will be better?
No, that's my question. If you get a classification map, the first one which you showed in the previous step, go back one, this one.
So
This one. Is this classification map independently calculated from the next classification map which you have on the next step at the same time?
oh yes, they are independent.
So they are calculated in parallel.
Yes.
Can be calculated.
Yes.
Then you get the results and you average.
Yes. For each ROI, we average them, but for different ROIs, we cannot merge them.
I understand that. So my question is, as long as you have some quality assessment, is averaging all of them, I know the government of it, but is averaging all of them the best, or can you have just have some number of the best results and average those? You probably have some good results and some not so good results in this set. Something that averaging everything is a good idea.
I see. So when we average them, we just not use the equal weights. We also consider the appearance similarity between for example, the training image and the testing image. So we consider this when we do average.
That makes more sense.
Okay, thank you very much. Let's thank the speaker.
Thank you.